Well, thank you all so much for coming to hear about Mars. I love Mars. It's probably my favorite planet. I like Earth too. But, so before I start, I just want you to know that, please, if you have any questions at any time, feel free to just shout them out. This can be more of a conversation. If you don't have questions, that's fine too. But I just wanted to let you know. And let me know if you can't hear me. So, excellent, this works. Okay, so you did hear a little bit about me, but I thought I'd tell you a little bit more. So I am a geologist, and I'm also a planetary scientist. So that means that I study rocks on other planets, specifically Mars. So I'm a postdoc at Los Alamos National Laboratory, and I think I didn't really know what a postdoc was until maybe I started grad school. So a postdoc, if you don't know, is somebody who's recently finished her PhD, but I'm still in training. So it's not quite like being in school, but it's not quite like being out of school quite yet. And as you heard, I am a science team member on the Curiosity rover, which is currently on Mars. And I specifically work on an instrument called ChemCam. So I'll tell you a little bit more about that in a bit. But first, I think we should start with some basics. So here are all of our planets plus part of our sun. I just want to point out this isn't to scale. Our planets aren't this close. But does anyone know, where do you think Mars is on here? You can just shout it out. Like here, I'll start. Yeah, where do you think? Here, I'm going to put where? To the left of Earth. Wait, which left? Your left.
It's a fourth planet.
That's right, it is. So I think that's what you were saying too. So that is right there. So Mars is the fourth planet from the sun. So you can see that it's actually one of our neighbors. So here's just some comparison on Earth and Mars, just so you know. So first thing you can notice here, right, is that Earth is a lot bigger than Mars. It has a diameter that's about twice that of Mars. So Mars is a little bit smaller. It's also quite a bit lighter. So I put the mass here. I just said one Earth. Say, if we were going to measure Mars in Earth weight, then it would be the mass. It would be about 0.1 Earth. So it's actually a little bit lighter, and not just because it's smaller. It's actually less dense, which means it's made of materials that aren't quite as massive. So Earth's day is about 24 hours long, as we all know. Technically, it's 23 hours, 56 minutes, but about 24 hours. Mars' day, which we call a sol, just to differentiate it from the Earth day, is actually a little bit longer. It's 24 hours and 37 minutes long. And so this is going to be important, so just remember that. So the day is just a little bit longer, but not that much longer. So now I'll show you this is a picture of 3 of our rovers in mock-up. So these are not the actual rovers, these are models, and they're at the Jet Propulsion Laboratory. These are some engineers for scale, you can see. So what you can see here, so this is actually in our Mars yard where we test our rovers. So we try to make it as Mars-like as possible. So it's red and filled with rocks like this. I just wanted to put this into context for you. So we've actually sent rovers before. So the first rover we sent was part of the Pathfinder mission in 1996. And that was this little tiny Sojourner rover. It's like a little Tonka trunk. Not very big, but it actually had 6 instruments on it. And then later we sent twin rovers, which you're probably familiar with, Spirit and Opportunity. So those were launched in 2003. And they're a little bit bigger. So that's right here. Oh, please.
So did Pathfinder have like a camera so you could take pictures?
Yeah, there was a camera on that. So yeah, we had pictures, we had some chemistry data. It was actually a remarkably capable rover. The only problem was that it was actually still, it couldn't power itself, so it had to have a wire attached to the lander part. So it could only drive in sort of this radius around its lander. So it didn't have a big range, but we wanted to see if we could send something that would rove on Mars, and so that's why we did it.
Might as well just see part of it.
Yeah, you gotta try something before you know if you can do it. So that's right. So as you notice, right, the Curiosity is enormous. It's actually about the same size as a Mini Cooper car. Very, very tall mast here. And so the official name for it is actually the Mars Science Laboratory, and we call it that just because it's like sending an entire laboratory. We have a lot of experiments that are very powerful. So this is the rover that I'll be talking about. So just to give you a sense of why we're going to Mars now and what we're doing, the goal of Curiosity is to assess the past and present habitability of Mars. So habitability is sort of, it's not looking for life, but it's looking for places where life, as we currently understand it, could exist. So we're looking for certain things, like water is very important for life as we currently know it. Nothing on Earth can live without water. But we're also looking for signs of water. So even if there's no liquid water there right now, was there ever liquid water? So we're looking for water-formed minerals and hydrated minerals. So those are minerals that have water in their structure. We're, of course, looking for organic materials because we are built of organic chemistry. And we're also assessing the surface radiation environment. So Mars doesn't have a magnetic field. So it actually has a lot more cosmic radiation coming in. So we're trying to understand what that would mean for terrestrial life forms, for example. How would that affect them? So that's what we're doing on Mars right now.
So by terrestrial organisms, you mean astronauts, right? I noticed that we don't care about so much how random terrestrial organisms would fare on the surface of Mars. Isn't the real question how are people going to do? What are people going to need when we get there?
I mean, so yeah, for me as a scientist, I care about finding, I care about the big scientific question, but certainly NASA also is trying to assess this for a human mission in the future. So it's useful for both of those things. So yeah, that's a good point because every time we do a mission to Mars, we learn more about that planet, and that just sort of adds to our knowledge and helps us plan a future mission, whether it be manned or unmanned. So I just want to show you this artist's conception of what the rover looks like operating on Mars. And I've labeled all of the instruments that we have. I've highlighted my favorite one in red here. That's this one with the laser. But I just wanted to show you, and I'll tell you again more about that. But this is quite a powerful instrument. So we actually, rover, and we have a lot of instruments. We have an arm here that can actually reach out and touch samples. And we also have this laser, of course, which can sample at a distance, and many other things that we can do. So now this is the artist's conception. This is an actual picture of the rover on Mars that it took of itself. I love this picture.
How would it take a picture of itself?
Yeah, right, great question. So how would you take a picture of yourself?
Hold the camera out like this.
That's right, and that is exactly what this rover did. It has a camera on its arm, which you can't see in this picture, and that's because it's taking a picture of itself. So this is the arm, and it would be coming out here. So it held up that camera, took a selfie. Sorry. Why? Because we asked it to. That's a really good picture. Then no one's going to, people already have a hard time believing that we went to Mars. Then they're really not going to believe it. Sure.
So I don't see the arm coming out. Did they put the camera down?
No, so the arms, let's go back to the other slide. So the arm's right here and has this big, there's actually several instruments on that arm. But what it did is it held it up like this and then took a series of pictures. So the arm is not really visible. See, I think they might have blurred out part of it, but this is actually a mosaic, so it's a picture made of pictures. So it's, the arm is partially in some of those, but mostly not, because again, it's doing this, taking a picture. But this is what it would look like. This is the arm that took the picture. So yeah, that's a good question. And I'll tell you more about that process, but there's a team of 400 scientists that I'm part of, and we get to decide every single day what we want to do with the rover. What kind of science do we want to get? And so we decided that we wanted to see this rover on Mars. We have never had the opportunity to do that because the other rovers didn't have arms like that, or at least not with this capability. So honestly, we just thought it was a really cool picture. So we can work together. So I don't work on the hand lens imager, which is what took this picture, but the folks who work on that wrote a sequence. It was basically computer commands. And then we talked to the people at JPL, and we sent them up to Mars when we decided they were ready. So that's how we do it. But we all agree on what we want to do every day, which can be difficult if there's 400 people. So I just want to now show you again the greatest instrument ever. ChemCam is right up here. This is an actual picture of it. Actually, so these are the mast cameras right under it. So these beautiful pictures that you often see will be taken by mast cam. But this is where the laser is housed. And this is what it looks like when it's not in that housing. It's actually plated in gold. And this is where the laser comes out. And I also wanted to point out one more thing. So Los Alamos was not just involved in building this instrument. It was built at Los Alamos. But we're also powering the rover. You might notice there's no solar panels on this, right? There's no solar panels anywhere. And the other rovers have had them. So this rover is enormous. And solar power is not very efficient at this distance from the sun. So it's actually all nuclear powered. So it's powered by a little lump of plutonium that came from Los Alamos. So yeah, this will be going for quite some time.
Wouldn't the plutonium run out after a while?
Yeah, but it's going to be a long time. It's probably going to, the wheels are going to fall off this thing before it won't have enough power. Yeah. And it's a little bit better. So the solar panels, they can work, essentially. Could the rover talk? Well, we can sometimes play with the servo motors on some of the instruments and play songs. I don't know if you've seen this online, but you can tune the motors in some of the instruments. But generally speaking, we don't do it, just because it would be a use of power. That's as much as it can talk. Though we did uplink a Will.i.am song, and then it played it back to us from Mars. So that was kind of fun. So it sang to us in some ways. So this is what people usually think I do. Rover, laser, huge explosion. Essentially, this is what I do, but it's on a slightly smaller scale, a little smaller.
I thought the laser was supposed to be red.
Well, that's a good point. That's a good observation. So,
The other picture is red.
so the laser is operating at a wavelength of 1067 nanometers. So I don't know if you guys have done this in school yet, figured out what colors are of light that would correspond to, but that's actually in the infrared. So in fact, it's not red or green. It is invisible. That's right. But it doesn't look good to have this invisible light. This picture looks a lot worse when there's no laser. So they just drew it in green.
I can definitely tell that is fake.
Yes.
So it's like, no, it goes red on Mars, blowing.
See, you're smarter than a lot of people. Because I posted this on Facebook, right? I'm like, hey guys, ha ha ha. And one of my friends from college was like, is that a real picture? I was like, you are kidding, right? And she's like, no. Okay, maybe, why not? I mean, I wish we could get this kind of picture. I wish our instrument did that. It's a little smaller. So let me tell you a little bit about what actually my instrument really does. So this is a little bit of a better artist conception. So how this works is we have a laser that we can shoot at a target. So at a distance from the rover, we can shoot up to 23 feet away, so pretty far away. And we heat it up so hot that it vaporizes. So it's just, yeah, really, really hot, but only in one really small spot. It's actually hotter than the surface of the sun at that one spot. But that's only maybe, a millimeter in diameter. So then, as you might imagine, it makes a really bright light. And we can collect that light back here in our spectrometers, so that's something that will collect light. And we can actually figure out what this target is made out of, because it turns out that different elements emit at different wavelengths. So different colors of light can tell us what is actually in the sample. So here's just, these are actually photographs down here at the bottom of just different things that we've shot. These are kind of stretched, but you can see this with your eye. You can actually see that aluminum does look bluer. These are actual plasmas taken in the lab. This is copper. And these three come from a rock called basalt, which is actually made up of many minerals. So depending on where you hit it, you're going to get a different color. So we get two different data products every time we shoot a rock or soil on Mars. We get this spectrograph. So what this is a wavelength here on the x-axis, so that's the color of light. And this is the intensity, so that's how much light do we get at that particular color. And you can see that we don't actually, we can see that we actually have spikes at certain places, and so we know what those correspond to, and that's how we know what the elements are in the rock. But we also get a really beautiful high-resolution image of where we shot. So you can see here, this is some holes that we made, because again, we're vaporizing material. So we did 5 little holes here. And this actually helps us understand how the chemistry relates to the geology. So where did we hit on the rock? Did we shoot a white mineral? Did we shoot a dark mineral? That's actually very important. So this actually helps us put the chemistry into a context that we can understand. So before I want to go on, I just want to point out this is not just a US effort, although it was led by Los Alamos, which is actually a joint project with the French Space Agency as well. So this is actually one of the great things about having a French side of the team, is that you get to go to France all the time. So we were there we went to Toulouse this May, and this is our team picture. There's a model actually of the rover here, full size, and we're totally blocking it because there's so many of us. I just want to point out though, so just for fun, I just took a look. I counted, there are 12 women pictured here. And there are 47 team members here. So that's actually, it's not the entire team, but it's almost the entire team. And that's about 25%. So, that's not bad, but that's definitely not half. So I would say, again, I would encourage everyone to go into science. And our male colleagues are great, but there's definitely a lot of room for improvement here. We could definitely use a few more women here. So young ladies, think about that. I'm this joker right here. I don't know what I was doing. I was like, ooh, I'll just recline in the front. Nice, I know.
You're in France.
I know, right? They're relaxed there. Okay, so let me tell you a little bit about where we went on Mars. So what I'm showing you here is a topographic map of Mars. So the warmer colors correspond to higher elevations, and the cooler colors correspond to lower elevations. And so we went to a place called Gale Crater. And that's right here. So one thing that you probably noticed, right? Oh, and if you want, just for fun, this is Olympus Mons, which is the largest volcano in the solar system. It's quite tall. This is Valles Marineris. And just for scale, so that's a very big, it's a canyon. That's the width of the United States. So that's just to tell you how big that is. It's quite large, yeah. And some of the other important landing sites or suggested landing sites are also marked on here. You can see, so Opportunity is here. Spirit is here. It's not that close. We probably are not going to go visit, but we could. Conception. This one? Which? That's a crater, yeah. That's the Hellas Basin. It's this, we think that it is a very ancient impact. That was a really big impact. That probably messed Mars up pretty good. But so you probably noticed, so right, you see that the southern hemisphere is filled with craters, right? That's what all these little holes are. But the northern hemisphere is very, very smooth. That's kind of interesting, right? That's very, very different.
And the northern hemisphere seems to be like lower elevation than the...
Exactly. It's lower elevation, it's smoother. So one of the things we know, just in planetary science, we know that, for example, the moon has had a lot of impacts, so it records, its very ancient history on its surface. The Earth has had just as many impacts, but we are constantly resurfacing, so we don't see as many impacts on our surface. But they've happened. So we know this is a newer surface because there just aren't as many craters. And one of the ideas that has been put forth is that this could have been an ancient ocean. So Mars could have had an ocean that was all along the northern hemisphere. And so this would have been, but it's gone now, of course. But that is one explanation for why it looks so different. And we might have had maybe a volcano, you could say, could put lava onto the surface. But we don't see any volcanoes that are big enough. This is the biggest one. We know where all its lava went. It's like right here. So it's a question we haven't answered yet. But one of the reasons we wanted to go to Gale Crater is, as you can see, it's sort of on the boundary between this newer, lower surface and this older, higher surface. So that's one of the reasons we want to go there. Because again, water is really important to us. We really want to understand the history of water on Mars. And this is a great place to see a large swath of Martian history. So here now is I'm zooming in. This is the crater, the actual Gale Crater. And what you can see is there's actually a big mound of material in it. And it's the size of Kilimanjaro, which is a very tall mountain. It's the tallest mountain in Africa. It's about 19,000 feet tall. So that's that's a big mountain. And so we see from orbit, and also in this picture that the rover took, that this material, the mountain is made up of these layers here. And for geologists, layers are really important because usually they're not made except by water. So we are viewing this as sort of a Martian, Grand Canyon, where older materials at the bottom, younger materials are at the top. So as we drive up the mountain, we can learn about the history of the deposition of these materials. We also have seen some water-formed minerals from orbit. So that's why we chose to go here, to see this mountain. So it's called Mount Sharp. Oh, and just so you know, so this is actually really big. This is only the edge of the mountain. This little boulder here, which you can barely even see, it's like 1 pixel, that is the size of Curiosity. So from where the rover was sitting when we took this picture, that's really far. So we've got a little ways to go before we can get to the mountain. And I just like to show this picture because I think it's cool. So this is actually Curiosity as it was landing. So this is its little parachute. Here's its pod. And one of the orbiting satellites took a picture while it was landing and actually captured it. I know, that's really cool. I can't believe they did that. Yeah, that's pretty amazing. They had to plan it for months. So I think Yeah, so the next thing I'm going to show you, so I'm alluding to some of the landing. The landing is actually really interesting. So I wanted to show you some videos. I think I'm going to have to play it from over here. Okay. If I'm lucky, the embedding will work. If I'm not, it won't work. So before I start this video, this video will show you two things. The beginning is a simulation, so it shows you an animation of what the landing was supposed to look like. And then the second part is the actual landing as seen by the rover, taking a video. So you can see what's going on. So let's see if that can work. You gonna work for me? No. Ooh. It's okay, we're gonna get this. Okay, so here we are, we're leaving Earth. Wait, I'm gonna pause this, I'm gonna make this bigger. Okay, so this is just after launching. It's separating from the rocket. It's flying away. And now 8 months later, we're on Mars, so that was a kind of a quick cut. So you can see now that it's in this pod, and it's using the atmosphere to slow itself down. So that's what that's aerobraking. You can see there's some little shooting things here. That's actually us steering. We were able to steer this, this rover, which is the first time we've been able to do that. So now it's popping its chute, but Mars actually has a very thin atmosphere, so that's not enough to slow it down. So there now, the rover can see the surface, so that's where the next video is going to start. This is a scary part. Then we're going to drop down on what's called a sky crane, which we had never tested, of course, because we couldn't. And theoretically, it was going to gently lower the rover to the surface, you know, and then, then it would detach itself, and then it would go away, far away, so it could crash somewhere else, not right on the rover. Yeah. So yeah, and then yes, and then we could start our operation. So now here's the actual video, and the sound you're going to be hearing is actually from the flight room. So that's the back shell being popped off. See, now we're still really high in the air because that's getting really small and it's still falling. These are sand dunes right here, and you can't see the mountain, but the mountain is out of frame over here. So yeah, now we're going to fast forward because there was a lot of falling. So we're really excited because now we have powered flight. We're on that sky crane with those retro rockets, and the surface is getting closer. So just so you know, so I was at JPL at this time. We were in the basement where they keep the unphotogenic scientists. We were not in the videos, but this is time delayed. So we didn't know that the rover had landed successfully until 12 minutes after it had either landed or crashed. So it's a little nerve-wracking. So now you can see we're getting a little bit closer. We're kicking up dust now, so we're really close. I think they say here it's like 5 meters from the surface, so about maybe 20 feet. So now the wheel came down here, so we're ready to land. And you'll see we kick up so much dust that it gets very, very dark, and it's going to be really hard to see. But what's going to happen is, so yeah. So this is the part where we're just like, because if it crashes, then we're all out of jobs. But now you can see, so as the dust is clearing, there's this little ray of sunshine, and now we can see this is the surface of Mars. We have landed successfully, yay! And those are some pebbles that we landed on. So needless to say, once we figured that out, we were really excited. Yeah! So again, this is where they put the attractive engineers. We were also doing that in the basements in a different building. It was August 5th, 2012. Yeah. So, okay, so there's a scientist. I thought, everyone's always like, oh, did you get a blue shirt? Were you in that room? No, but here I am. And you'll see what my shirt says later. It's a ChemCam shirt that I made. I'll show you later. We were very excited, to say the least. I'm very relieved. And you can't really see, but this room, again, is filled with people, the 400 scientists I was referring to. I didn't actually have a seat. That's why I'm on the floor. So this is what the view was from our landing site. So there's that Kilimanjaro mountain, and it's a great view, right? This is beautiful. There are those dark sand dunes that I showed you in the landing video. Yeah, this is the shadow, of course, of the rover. And now this is something that we thought was really interesting immediately. So you see this sort of gray patch here? So that is a scour mark made by the retro rockets as we were firing. So we kicked up a lot of dust, and that's exposing rock. So everyone says, you know, Mars is the red planet, right? Well, under that dust, it's not so red. So that's already a really interesting science result. You know, what is underneath that red dust?
Did you laser that?
We sure did. Let me show you a picture. Yeah, so what we found, we drove over there, right? We're like, what is that stuff? Because we can do that, right? We get to decide every day. We're like, where do you want to drive? Let's go there. So we see this. So if you saw this on Earth, right, this looks kind of like the sidewalk or something, like some concrete. You'd walk right past it. But it turns out this is what's called a conglomerate rock. So this is a rock made up of rocks. So how this forms on Earth is that you have pebbles in a stream bed that gradually become cemented by another mineral that's precipitating from the stream water. So you can tell, you know this because these are very smooth pebbles. So I just happened to have done some research on a conglomerate on Earth, and so this is a sample that I took. This is actually from Utah, and you can see it actually looks really similar. It's actually similar in scale, even though this image is a little smaller. It looks almost identical. So right there, we've discovered, I mean, that's not just any flowing water. That's over a long period of time. We're talking at least hundreds, if not thousands, if not millions of years. So that's a really big result. So already in our landing site, we found abundant evidence that this area was filled with water. So that's a very habitable environment. So that was a really exciting result. So our instrument, of course, we can.
Is that the picture on Mars or Earth? That big picture.
This big one is Mars. That's a great question. This one is Earth, because my thumb is there. Yeah.
It's like there's an alien on Mars.
I know, right? Ooh, got to crop that out. Don't want anyone to know. No, that's not true. No thumbs yet. We'll keep you posted.
That picture was really interesting because it appears that there is, and this is my question to you, it appears that there's red dust on top of the rocks that are there.
Yeah, that's right.
So where did that dust come from?
So that's a great question. So it turns out that Mars is a very dusty planet. And it has global dust storms that will, every Martian year or so. So that's every 2 Earth years, essentially. And so there's this red material that appears to be very homogenized over the entire planet. So the wind is a really active geological process on Mars. It's probably the most active now since there's not a lot of flowing water. And so that can actually move a lot of material around the planet and appears to do so. It looks like from orbit that the dust is actually all the same everywhere, which is confusing because if you can't see under that dust, then you're like, is Mars all the same thing? No, it's not. It's just that it's covered by this dust. So that's why it looks red, but it's not necessarily because Mars is just filled with red rocks. Yeah. So actually, so that kind of leads me to something I was going to tell you guys about, another result from ChemCam. So I just wanted to show you some actual data so you can see what it is that we look at. We look at these squiggly lines all day. So this is the very first spectrum, and we took this on Sol 14. So again, 14 days into the mission after we landed on August 5th. Turns out that's my birthday, so I was pretty excited about that. This is a really good birthday present. I'm sure the project planned it that way. So you can see what we're looking at here is the spectrograph. So along this x-axis is the wavelength. So that's the color of light. And if you don't remember your nanometer colors, I've just put some boxes around here. So this is in the ultraviolet. You can't see that. This is sort of a visible or bluish. We can see that, so it's visible. And then this contains some red and near infrared. So some of this you can see and some of it you can't. So our camera can see all of those things. And so you can see that we have some peaks in certain places, and we've labeled some of them here. But I want to draw your attention to a tiny little peak you can't even see here. So we've put it in a box, so this is made a little bit larger. Now this is at about 656 nanometers, we saw a hydrogen peak. That's our very first shot right here. And now hydrogen is not something that likes to hang out by itself. And generally, it wants to hang out with oxygen. So what we found was water on the very first shot on Mars. That was the very first time we used our instrument Boom, we found water. That was such an exciting result. Now, it turns out that that water is related to the dust. It turns out all the dust is hydrated, so it has water in it, which tells us it was formed in part by water. Somehow, we still don't know exactly how, but that dust is all hydrated, all that red stuff.
So is the dust red from copper? Or what made it red?
It's red from iron, so iron has been oxidized. Yeah, that's a good question. Mars is a very rusty planet. That's what it is. It's all rust. Yeah, it is, yeah.
Why is it called the ChemCam?
Yeah, so we call it ChemCam because it's short for chemistry and camera. So our chemistry instrument, that also has a camera. That's sort of simple, I know.
Can you get quantitative data out of that, or just qualitative?
We can get quantitative data. Requires standards. So if your sample on Mars is extremely different from your standard set, then, I mean, we can tell. We know immediately. But you won't get as good of a quantitative result. But we do quantification. So that means, though, we're able to say not only is there aluminum in here, but I can tell you how much aluminum, which is important if you are a geologist. It tells you something about the rocks and how they formed. So yeah, and I didn't actually point out, but this is our camera. That's our image that we took. And that's of this rock, and that's of this area right here. So this turned out was actually basalt, which is a black volcanic rock that you see in New Mexico. So it's something you could see here, except it's on Mars. So just to give you a little update, today is Sol 391. So we have been on Mars for 391 Martian days. So that's a little over an Earth year, but not yet a Martian year. And this is just our traverse map. It's actually not complete. So this is where we landed. This is, we named this after Ray Bradbury. This is the Bradbury landing. And you can see we made these stops. All these numbers are sols. So this is when we actually took some data somewhere. We stopped for like 150 sols here. And it was a really interesting place, but we realized that actually we had to get going. So we actually started driving pretty fast. Yeah, 150 sols, and this is like 10 sols. This is only 351. We're actually way down here now. And I'll show you why we started driving so fast. We spent a year of the mission going here. So this is in meters right here. Okay, so we didn't even go a mile in the first year. Oh, and so here, this is my next video. So you might wonder also, how fast can we drive, you know? When I say we're driving really fast, what am I talking about? So I don't have a video of the actual rover. How long did we? Or can we? We're still there. We're operating today. We got data right now. Yeah. Yeah, well, hopefully we'll last at least another Earth year. But I think we can do better than that. Yeah, so I have another video of the rover in the Mars yard that we use to test all of our sequences. Oh, stop. Yeah, it's at JPL, so I showed you that picture before. Okay. So, oh, I'm sorry, it's being so slow. This is me videoing, so not a great video, sorry. Can you hear that sound? That's the sound of a rover driving. It makes a terrible sound. Those are metal wheels. This is the guy that holds, so this one is not nuclear powered. It's plugged in with some very big plugs. That's the engineer. So actually, if you're nice to the engineers, they'll let you drive it with your iPhone. You can just command it, yeah. That day was like, we're a little busy. They were trying to get it to autonomously figure out how to drive itself home. They were testing, its autonomous driving capability. I think it did. The house that it lives in is like maybe, I don't know, 20 feet in to the right. Here, I'll play it one more time. You can hear that horrible sound. I always think it sounds like it's breaking. You know? Ugh.
How fast can
This is top speed.
That's as fast as drives.
But like how many miles an hour?
That's not even a mile an hour. Yeah, I don't even know. Yeah, really slow. Yeah. So we don't drive that fast. So when I say we're driving really fast, that is what I'm talking about. That's really fast for a Mars rover.
When you any prizes on the highway though?
Definitely not. Luckily, there are no highways. Okay, so we are not driving very fast, even though for us this is extremely fast. The reason we took off so quickly is because of this. So this is the landing site. That's sort of the area we spent forever in. This is where we are right now. And so we've been there for a year. This is how far we've gone. This is the mountain. We have not even gone to the mountain. And these are those sand dunes. We can't drive over those sand dunes because we might get stuck. So we actually have to drive around the sand dunes and then go to this break so that we can actually start driving up the mountain. So we sort of, like, we're having so much fun, like, shooting rocks on Mars that we didn't realize that a year had passed. So we have a lot more driving and a lot more science to do. So stay tuned. Hopefully we'll get here within the next year, right? Because we're not traveling that fast. But that's what our goal is. So there's going to be a lot more science to come. So we hope it lasts at least that long. Okay, so I just want to talk a little bit about driving a rover, because I actually had no idea what that meant. I was hoping there was a steering wheel, but there is not, unfortunately. I know, I was really disappointed. So this is actually our operations center in downtown Los Alamos. This is where we drive the rover from these very laptops. In fact, from the laptop I'm showing you this slideshow on, I drive the rover. So what that really means is that we're actually commanding, we write our spacecraft commands in Los Alamos, and then we can send them. We talk to people at JPL. We actually talk to our collaborators all over the world. And then we can decide on what we're going to do. And that's how we do it. We just do it from our laptops. Now, anywhere you have Wi-Fi, you can do this. Yeah. Okay, so I thought I'd just tell you a little bit. This is a lot of words, sort of boring. But I'll tell you about what it was like driving the rover, working on this project right at the beginning. So we all had to be in California at the Jet Propulsion Laboratory. So that's where all unmanned missions are operated out of. So we all moved to LA for 3 months, so the first 90 sols, and we had to live at a Mars time. So remember, the Martian day is a little longer than the terrestrial day, right? So what this means is that if you want to start at the same time every day on Mars, it's going to be 40 minutes later on Earth. Every day, you add another 40 minutes. So you might start some days at 7 in the morning. Eventually, you're going to be starting at 1 in the morning or 2 in the morning. It's like, yeah, you never sleep is what happens. It turns out we are really, really well cemented on Mars time, or Earth time, excuse me. We've all, lived our entire lives here. So it is, I found exhausting.
Confusing.
It was very confusing. I basically didn't sleep for 3 months. But luckily, that time is over. We're now back at our home institutions, and we're on California time, which is not so great for our French colleagues, but which is great for us. We only work 5 days a week instead of 7 days a week. Isn't that nice? So the way that we plan how we're going to do, what we're going to do with the rover in a day. So we have these long-term goals that are planned in advance. Like, for example, get to the mountain. That's a long-term plan. So we need to have some milestones that we're going to make every few months or so. But the daily experiments are planned by people like me. So how this works is we look at the data that we got yesterday, sol, and then we think, say, okay, what did we learn? Is there anything that we want to know more about? Do we want to move on to another sample? And then we decide on new targets for analysis or to target the old samples for more analyses. And so then we, as I was telling you before, we write these spacecraft commands in a special software written by NASA. And you think, oh, great, we're done. That's like before lunch, right? But no, we do not want to send up a typo. We don't want to make a mistake. So we have to actually check it over many, many times. Many people have to look at these before we'll send it to Mars. Because at the very worst, we could break the rover. And at the very best, we would delay the long-term goals. So I'm going to admit something. So I was on shift when we accidentally targeted with the laser the arm. We were going to shoot at the arm, but not because we thought the arm was there and we wanted to be funny. We actually wanted to shoot at a rock, which was where the arm was, but in our images that we got, the arm hadn't moved yet. So we were like, oh, we can shoot this. And so we actually targeted the rover. Luckily, the rover is smart enough. It's like, no, you're not going to do that. And it failed our sequence. We're like, great, awesome. But that's the kind of thing, is that even though we had hundreds of people look this over, that still happened. So we have some contingencies in place where that's not going to happen again. But it's really important that we don't break this instrument. We can't go back there and fix it, right? So we don't want to break it quite yet. So for me, what I think is the most fun part is that we have science discussions where we talk about, people who have been looking at the data for a while, come up with an idea. They're like, well, I think this means that, and what do you guys think? And that is actually really fun. We used to do that at the end of the sol. So again, that could be in the middle of the night sometimes. Sometimes it was during the day. But it was the time where we could really relax and just think about science. Like, what are we learning about Mars? And I loved it. And there's people people are free to say, any crazy idea, because that's how science is done. We don't know the answer. That's why we're doing this. So that tells you a little bit how we actually, what it means to drive the rover. So I just want to show you some pictures now. So this is when we were at JPL. This is one of the many meetings that we had to attend. And it was a little intimidating, I'll tell you that. So you can see every instrument has an assigned seat in this giant room. But we only get 2 seats, and our team, as you saw, was extremely large. You can see there's a huge cluster of people right here at the end. It's like our 5 people that we jam in there. And so when you report, you'll be called upon to report upon the state of health of your instrument and the data. Did it come down? Is it correct? And you have to actually speak in microphones, these little microphones that come out. Even if you're talking to the person right next to you, you got to talk into a microphone because people are on the phone listening. And I actually found that to be kind of intimidating. Just especially when you're, it's like 4 in the morning and you're exhausted. You're like, do I even make any sense? Hello? So I spent a lot of time in here, especially on the floor down here when there were no more seats. You can see there's a lot, we project a lot of different things up here. This is where management sits. They're not in that picture. This is a great picture my wonderful French colleagues took. This is me. I was on shift, and it was 5 in the morning, and we had a meeting starting at 7, and I was just dying. I was like, I cannot do this. I'm so exhausted. I was like, guys, I'm just going to crawl under this desk, take a little nap. So they thought it'd be funny. So this is me. They put my badge here so that no one would be confused. They're like, this is Nina Lanza sleeping under the desk, I was lucky because I had a friend at JPL who actually had a sleeping bag and a pillow. Yeah, because otherwise I would never have made it to that meeting. But it was not all toil because the project provided free ice cream. Awesome. I didn't know about it until like a month in. I was like, where is all this ice cream coming from? They're like, you didn't know? This free ice cream. You can get 1 ice cream a day. I think somebody was taking more than their fair share because they only refilled it once a week, right? It looks pretty empty, and this is like a Tuesday. I'm like, somebody took my ice cream here. But so for example, after I woke up from that nap, I went and got some ice cream for breakfast. I was ready to go. It is the breakfast of champions. So here's another fun thing. So because you're coming and going at really strange times, and you're kind of in the mountains of Pasadena, there are a lot of animals there. These little guys are not that little, and they were really insistent that I not go to my car. My car is like this direction. They're like, oh no. This guy was sort of stamping. I was like, I don't know what I'm going to do. I don't know.
Those aren't your French colleagues?
No, I know, right? Hard to tell, but I know, what's up with their eyes? They're crazy. Yeah, so I had to stand there for a little while until they decided to, I don't know, just keep walking. But that was kind of fun because you don't see that during the day, and we're in the middle of Los Angeles, so you don't expect that. You might expect that here in New Mexico, but that's a little weird for out there. We also, again, had a lot of time being exhausted, so we spent a lot of time making fun things to put up around our operation room. This is the ChemCam ops room at JPL. This is an instrument called REMS, which is a Spanish instrument, and it's a weather station. And then the ChemIn instrument is over here. So, somebody noticed that half of our team is French, and this is a Spanish instrument. So there's a mountain range that separates France from Spain called the Pyrenees. Somebody hilariously put the Pyrenees up here, and that just started it. It's just like, so then they put all these pictures of like Spanish wines and cheeses, and then the French put this here. I was like, we're not going to be outdone. So the Rockies are right here. You might recognize this is the isotopes, yeah? I put some chilies here. So I was like, don't forget about the US side of the team, guys. But there was a lot of photoshopping going on because, lasers are pretty cool, and we have an instrument that shoots lasers. So, for example, this was on my shirt. This is the shirt I was saying. This is the ChemRex. This is the Chem Destroyer. This is actually really apropos, with the laser. This is the one, our French colleagues, yeah. So our French colleagues, they speak English very well, but they don't necessarily know all the sayings in English. And they were like, why do people think our instrument would hurt cats? It was hard to explain. I'm not sure. That might have been a cultural misunderstanding.
The rat ones.
Oh, yeah.
That's what the cat's for.
Yeah, right, exactly. But now we destroyed, so now the rat's fine, yeah. Okay, so I think hopefully I've shown you that this is actually the greatest job ever. This is my dream job. I love this, and it's really fun. It's a lot of work, but it's also a lot of play. So I thought I would just tell you a little bit about how did I manage to get this greatest job ever. So this is just a brief history of my life here. So I first became interested in space when I saw Halley's Comet. I saw it through a telescope. My parents took me to an outreach event, and it was the first time I had ever thought of the sky as more than just a dome. It was actually space, and there were things in it. And I loved that idea. That was amazing. I loved it so much that I actually ended up majoring in astronomy as an undergraduate. I went to Smith College, as you heard. Now, Smith College is a women's college, and so all of you ladies out there, don't be afraid of going to a single-sex school. I loved it. It was a great experience. But so even though I loved space and I really enjoyed school, I wasn't sure about grad school for a really bad reason, because I didn't think I was good enough. I mean, that's not even a question you should ever ask yourself, okay? It should always be, is this what you want to be doing, yes or no? If the answer is yes, then keep going. So I was lucky enough, though, to have a mentor who, so I told her, I was like, I don't know about grad school. And she's like, well, okay, what is it that you really love learning about, even when nobody makes you do it? Like, what do you like to do, in your own time? What do you want to learn about? So I decided to take a very honest look at what I liked. And this is a real list. I sat down. I made a list. I really like science fiction. Nobody makes me read it. I read it all the time. Love it. I also really like spaceships. Spaceships are awesome. And aliens. Wouldn't it be great if we could find some aliens? So this is my list. This is the list of things. But from that, I decided, I was like, of course, I should be studying Mars. Obviously, all of these things are encapsulated in Mars. So then, at that point, I said, okay, let's do this. So I called up, actually just called a researcher at Lanza. I had no idea what I was doing. And I just asked him for a job. I actually called him every day for like weeks. Poor guy. But very nice. He ended up letting me do a post-baccalaureate job. So that's after college, but before you go to grad school. And I really enjoyed it. I loved it so much. I actually ended up going to grad school, although I realized I was doing sort of the wrong major because I wanted to study Mars, so I needed to know something about rocks. So I changed to geology instead of astronomy. So I got a master's degree at Wesleyan University, which is in Connecticut. And I did a master's first because I was like, I don't know if I want to commit to a PhD in a subject that I've never taken. Like my first geology class ever was in grad school. But I really did like it, so I ended up going to get a PhD at our very own University of New Mexico. And I chose UNM because my advisor there is a co-investigator on ChemCam. So he's like, would you like to work on a spaceship? I was like, sold. I didn't even wait to hear from another grad school. Yes, I would. Thank you. Okay, so now you're like, okay, now you know how I did this, right? But you're like, okay, I missed Halley's Comet. How am I going to do this? So how can you do this or whatever it is that you want to do? Maybe it's not exactly Mars. Whatever it is that you have your eye on. I just want to emphasize this. You do not need to be good at it. You just have to love it. Okay, nobody's good at anything when they start, really and truly. So you might have heard this idea that people who are experts have to put in 10,000 hours of practice before they become an expert. Okay, so let's say you work 40 hours a week, take 2 weeks off for the holidays. Okay, that's 5 years of full-time work to become an expert in something. And that's the bare minimum expert. Okay, so that takes a lot of time. So you probably haven't had the time to do that, and that's okay. But you can learn anything and be good at anything if you put in the time. So if you're willing to do that, you can do it. And just don't forget that research is about answering questions that we don't have the answers to. We have no idea. I mean, like we saw, that rock on Mars, we had to figure out what that was. No one knew the answer in the back of the textbook. We had to figure it out. So you're not actually dumb if you don't know the answer. Now, that's something that I was always afraid about, like, oh, if I don't know the answer, I must not be good enough. That's not true at all. Nobody knows the answer, so everyone's just as dumb, I guess. And I also want to point out that you can actually be really good at research, scientific research in particular, and not necessarily at school, because those are really different kind of things that you're doing. In school, you have to, learn material that people tell you to and spit it back at them. And, you can be really good at that, and that's great. I wasn't actually all that great at school, but I'm very good at research. So just keep that in mind, too. Just because maybe you find that school is challenging doesn't mean you can't go to grad school and drive a spaceship. I can. So even though, I just want to also emphasize, too, even though, yes, you can do anything, expect to work hard. Do not limit yourself just to the things that are easy. It might be, you might, say, okay, well, I'm kind of good at this, and even though I don't love it, it's something I'm good at, so I should stick to it. If you don't love it, don't do it. It's not worth it. It doesn't matter if you have to work hard. You're going to have to work hard to be good at anything. But I think the rewards are really worth it. Again, let me mention that I drive a spaceship. And be persistent. It's not, again, it's going to take you a long time. Don't be afraid of that. Just put one foot in front of the other. So I just wanted to throw that out there, because I don't think I knew any of those things until I was well into grad school. So with this, I'll end now. This is actually something this is our Marvin bobblehead here. We're actually shooting it with the laser. We're shooting him. See, he threatened us first, though, so now we can actually shoot back. So anyway, with that, I'll take any questions you might have.
Before
we have questions.
Cool.
So I handed out, as you noticed, these pink sheets.
Yeah.
Just real quick,
Yeah, sure.
I love the cat background screen. Is there any way you can share?
What you would like?
You know, the
Curiosity killed the cat?
yeah.
I'm very happy to. Actually, so I put my email on here. So if you send me an email, I'd be happy to send you that picture. In fact, if anybody has questions that they think of later, don't be shy. Send me an email.
Do you know, I really thought that Curiosity exploding that big thing was really funny.
Isn't that funny?
No, it's like the aliens send another Curiosity and like the Curiosity Wars. No, the Mars Wars.
I know, sadly, we would probably lose because we only vaporize like this. Unless they're very tiny aliens, we would never be able to defend ourselves. And we move pretty slow. Sure, do we have, I think you were. So is this my first project with a rover? Yes, it is. It's my only project with a rover. I started grad school knowing that I wanted to do this. But I hope that I will be able to do the next one. We'll see.
Okay, we have time for one more question.
Oh.
What is the structure of the rover, the main frame? Is it titanium, aluminum, or?
It's titanium. Yep. I'm not, I guess I can't tell you exactly what alloy it is, but yeah, titanium. Do we have time for another question or not so much? Well, I can stick around.
How do you identify the unknown elements?
By unknown, do you mean elements that we have never seen on Earth? Yeah. I'm not sure that we know that those exist, right?
No, we periodically find a new element, and then you come up with a new element and things, right? In Mars, we do not know is there an element known to us. So in that case, how do you identify on your other scales? How do you come up with a new one?
So I think, okay, I'm just going to repeat the question for the microphone. How do we find elements that we don't know of on Mars? So the elements that we say, when people say, we've discovered a new element, those elements are not natural. Those are made in reactors, right? And they only exist for very short periods of time. They're not stable enough. So they are real and they get names, but they can't exist in nature for any amount of time they could not be part of a rock, for example. They're not something we would see. So the elements, in fact, the solar system is mostly made out of, the same stuff everywhere, right? In fact, astronomers generally say that the universe is made of hydrogen, helium, and everything else. And everything else, of course, is very important to us. But it's not a lot. Those are the trace elements. I mean, we are the trace elements of the universe. The answer is that the chances would be, I can't imagine that there would be anything that would be there. Yes, exactly, because I don't think it could last long enough.
It's just curiosity.
Sure, curiosity, we like that.
Okay, so we're going to have our drawing.
I'll stay here. I can answer questions after.
Let me just, what?
We thank her and applaud.
Oh, well.
Thanks, guys.